This is number 8. And it is talking about the characteristic set. Okay, and this characteristic set is more like the center of a tree. So it is pretty much the center or central part, I would say, center of a tree. Okay, what does that mean? We know we try to cut the graph into 2 parts, right? In the earlier session, maybe just last week, that we know that there is a certain way to use the Laplacian matrix to cut it. And so that you only cut a few edges, but somehow you have a balanced partition. The 2 parts are about equal size. And that's the same thing. Usually we look at this part and we say, okay, we will cut it at the center. Okay, but this idea is a little bit vague. So today we will introduce a few different ways to talk about the center of a graph. And well, they are of different definition, and the properties are different, but we will see that they have a unified theorem to talk about this. And actually, this is also what we see in the seminar course. Okay, if you have heard of this, that's something we have seen before. Okay, so the question is, where is the center? Okay, this is a vague idea. Okay, where is the center of a tree? We only focus on a tree, but in general, you can talk about the graph. Although the theorem we are talking about only applies for tree. Okay, so the idea, just try to find a balanced part, a balanced pivot. Okay, and pivot just means you will see later. Okay, so imagine that you have a stick. Okay, and then you put a pivot here, or just you put your finger there. Okay, and you have a ruler or a stick, and then you will see that, okay, this is too heavy. Right? It will tilt to the right hand side, right? So it will go this direction. So if this happens, then move the pivot to the right. Okay, so you move the pivot to the right a little bit, and so maybe it looks like this. And it depends on the depends on the density and the mass distribution. Probably here is the balance point. You don't know. It's not necessarily the longer part is the heavier part, but let's say it is still heavier. Say this is very heavy, but this is slightly heavy. Then we do the same thing again. So we move that to the right again. And you know, we are not always lucky. Sometimes we just move it to here and then realize that, okay, this time we do it too much and it is way too heavy on the left hand side. And this time we move left. And so whenever this happens, we know that the center is actually just around here, right? We will see that center is about here. So that's the idea of finding the center. And we will use this idea to do that on a graph, and particularly on a tree, so that the algorithm can work. So let's see what we can do. In order to talk about which one is heavier, we need to talk about the weight. And we want to talk about, let's come back here a bit. We want to talk about the weight of this part and weight of this part, right? And if the whole thing is a tree, then we will take out one vertex and then look at the weight of one branch and the weight of the other branch. So let's talk about what is a branch. Okay, so let's say T is a tree and V is a vertex, and each component of T taking out V. Okay, we have several parts, and you take out V, take it out, and then you will see that this part, this part, this part, they are called the branch. Okay, and each branch usually has a vertex, a spatial vertex. If this is a vertex V, then usually each branch has a vertex called U that is adjacent to V. Each branch has a unique vertex that is adjacent to V. So branch can be viewed as a rooted tree with root U. Okay? Each part can be viewed as a rooted tree, and the root is the unique vertex that is adjacent to V. Okay, now we can define a few more things. A weight function. This weight function is a bit different from other things. Okay. This weight function on a tree is the following. It takes every branch to a real number, and this real number should be positive. Right? Every branch has a weight, and later on we are going to use the weight to determine the balance point. And this function has to satisfy the following property. If a branch, let me do that first. Okay, so if I have two branches, F1 and F2, and if the vertices of F1 covers the vertices of F2. Okay. So by branch I mean this one is a branch. This is F1, but if you take only a part of that, for example this part, this is F2. Okay, so F1 is greater than or equal to F2, but not equal in this case. Covers, but not equal. And this is usual because bigger branch usually have heavier weight, right? The whole tree is heavier than just one branch. Okay, so we have this inequality to make sense. Now we are able to do the thing. Okay, so let's see some examples. The first one, we consider the weight, WV, okay, and it will send each branch to the number of vertices on the branch. Okay, what does that mean? For example, if we have a P4 like this, then we put a pivot here. Okay, and then we can consider the branch on the left, branch on the right, and this branch has one vertex, so the weight is equal to 1. The weight is equal to 2 on the right hand side. So in this case, we will move the pivot to the right hand side. But once we move the pivot to the right hand side, you will see it is symmetric. And this time, the left hand side is heavier. So we want to move it to the left again. And if whenever this happens, it is left and right, and it just cannot stop. And in this case, we will say both of them, this is called the central part. Now let's look at some more example to make it more concrete. Now you might say that, okay, that's for path, and for path, of course, I know where is the center. Now how about this one? You can do something stupid like this one. If you put the pivot here, of course, there's only one weight here, one branch here, and the weight is equal to 4. And so you want to move the pivot to the inner part. And once you move that, you will see that the pivot is here. Now you got 3 branches. This branch has one vertex, and the 2 vertices. Okay, so again, the left hand side is heavier. So we want to move it to the left hand side. Okay, now we see the weight. After moving the pivot, then we got two branches. The left hand side is equal to 1. The right hand side, the weight is equal to 3. So the right hand side is heavier, and we want to move it to the right. Okay, so again, you see this kind of behavior happens again. It is coming to the left and coming to the right, and left and right, left and right. So in this case, we say this is the center. Okay. Let me give you one more example to illustrate the last idea I want to emphasize. Again, this is a tree, and then we put a pivot. Depends on your preference. Just pick one, and ideally you will go to this same central part. Okay, the weight is equal to 1, the weight is equal to 4, so it will move to the right. But now this one is a bit different. Once you move to the middle part, and then you will see there are 3 branches. The left hand side is equal to 2. The right hand side is also equal to 2. But the middle part, the upper part, has weight equal to 1. So you will say that, okay, this is a bit weird. I don't know how to say whether it is balanced or not. But in this case, we say, okay, it has 2 heavy parts. Like you see, most of the case earlier, you only have just one heavier part, the most heavy part, and this is the same. Heaviest is on the right. Heaviest on the right, but this one, the maximum weight among all the branches is equal to 2. But there are 2 branches that achieve this maximum weight. So in this case, we say, okay, we stop here. It's okay. We call this as the central part. Now, let's move on to the next example. We can consider another function that will send the branch to the longest distance from the root. I will show you what does that mean. Okay. Let's use the same example as earlier. For example, if we take this one, then we have one branch, and this is the root. Okay, and then how long is the farthest vertex to the root? 1 and 2 and 1. Okay, this one has distance 2. So the weight of distance is equal to 2 on the left hand side. So we only care about on this branch how deep it is. So we move that to this direction, which is expected, and put it here. Now we got 3 branches, and it shouldn't be hard that this guy, the weight is equal to 0. Yeah, it's a bit weird. Anyway, let's call that 0. They violate my definition, but that's okay. Because I say all the weight should be greater than 0. But I think it is okay here. So you will see that the left hand side is the heaviest, and you will move that to the left. Okay, yeah. And we have the same behavior. After you move in that, this part is equal to 0. This part is equal to 1. Okay, so you will move that to the right. So again, we call these 2 vertices as the central. So the last thing I want to say is there is one that's called a WP. Okay, is sending the branch to the spectral radius of the bottleneck matrix. Okay, so after this one usually requires the help of the computer, so I will just let you know there is such an idea. But whenever you have the weight, then you can find its central part. And historically, in the literature, if you use WD, then the central part is called the center. So that's why we put a quotation mark on the center. That's because center actually has a particular meaning. Okay, and if you do WV, counting the number of vertices, then we call that as a centroid. And these are special terms in mathematics. And if you use WP, then it is called a characteristic set. And these 3 ideas helps you to recognize where is the central part of a tree. And so each of them has their own properties.